Right. Hey guys, alright, hope you enjoyed that short clip over there. So now you're able to tell how do you actually identify whether it will bend towards or away from the normal. So if this is vacuum or air and this is diamond, obviously the light ray will travel faster in vacuum than in diamond. So if I have a truck that is going down in this direction, you can see the right tire, left tire. Right tire here, left tire here. The right tire will actually enter diamond uh, first, and before the left tire. So that's why since it's in diamond, we treat this as a marshy ground. It will actually slow down, so that's why the entire truck actually bends towards the normal. Okay. So here are some refractive index of some common materials. You can see the value is always greater than 1, right? All right. Okay. So just to take note on something also, we are right now over in the next page for the example. Principal reversibility means that if I have a light ray will travel along the same path if the direction is reversed. Okay, this principle applies to both reflection and refraction of light. That means whether I shine here, my source of light is from here or here, it will go through exactly the same path. Okay, first example here using the first formula that we learned on speed of light, the ratio of speed of lights. Okay, if they gave you the speed of light in vacuum, that's 3.10 to the power minus 10 to the power 8 meters per second. Given the refractive index, find the speed of light in glass. Alright, so using n equals c over v. Okay, v is c divided by n, so c is speed of light in vacuum, and n is given as 1.52. So does it make sense for speed of light in glass to be slower than speed of light in vacuum? Definitely, okay, because in vacuum there's no resistance, that's why it's faster. So at least now you know this is just a quick check for your work before you proceed. Okay, the next one, let's use the other formula for refractive index. So again, n equals sine I over sine r. Just to take note, I is my angle of incidence in the, so it doesn't really, we don't really look at the arrows. Okay, it doesn't mean this is my angle of incidence. Okay, for example here, in this case x and y, you can see out the white one is this surface on the right is glass, is air, whereas the surface on the medium on the left is glass. So even though the light ray travels in this direction, okay, if I were to use Snell's law, that means the second equation over here, my angle of incidence is not x, it's y. Why? Okay, the reason is because my angle of incidence must be the angle in my less dense medium, okay, compared to this. Okay, this is more dense, that's why it's sine y divided by sine x equals to n. Okay, so sine I divided by sine r equals to n. So sine r, the rest is just mathematics. You can see I is given as 60, so I just calculate. So after you find out the angle of refraction, you can actually use the truck method to determine, oh, this will bend towards the normal, so that's why my angle must be smaller than 60, which is correct. So we are good to go. So since x and r are in alternate angles, r will be equals to x, which is 35.3. Okay? So principal reversibility tells you that it will go through exactly the same path since both of these are parallel. So y is also equals to 60. Alright, so we'll just go straight to the summary. You can actually look through some of these examples. Refraction is basically the bending of light as it travels from one medium to another, and the reason for that is because it changes speed as it passes the boundary of two optical mediums. Okay, the laws of refraction, okay, it's not it is important, but what's more important are the two formulas for refraction. Okay, first one, n equals c over v. Next, n equals sine I divided by sine r, where I is the angle of incidence in the vacuum or air, and r is the angle of refraction in the medium itself. Okay, so this is important. Alright, hope you enjoyed this second video. Next, we're going to touch on a little bit on total internal reflection. Okay, see you soon. Cheers.